Today we're starting chapter 3, so that last little dab of chapter 2 and then all of chapter 3 will be the unit that we're doing here. We're going to be talking about the derivative of a function, which is something that Wellington brought up last week. So if the slope of a curve, y equals f of x, exists at x equals a, and this is what we've been doing, we've been finding the slope of the curve, then this limit is called the derivative of f at a. So that's its name. You've already been doing it, we just now have a name for it. Okay? There's really two big ideas that we'll be doing, and they both involve limits. We're going to be doing derivatives, and later on, somewhere around Christmas, we'll be doing integrals. Those are the two big ideas in all of Calculus AB, just two. Okay? So not a ton. So the derivative of the function f with respect to the variable x is the function f, and you may miss this because it's right next to that p. That is, it looks sort of like an apostrophe, except it's straight. It's read f prime of x. So this little bit right here is f prime of x. Whose value at x is f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h, provided the limit exists. One thing to notice here, instead of just finding the slope at a particular point, what we're doing now is finding an equation for the slope at any value of a. So this will let us find the slope. If we needed to find the slope at 7 different places, we wouldn't have to do the limit 7 different times. We could do it once, find the formula, and then we can calculate any of those. If this derivative, f prime of a, which is the slope of the tangent line or the slope of the curve, exists, we say that f is differentiable at x equals a. Little bit of a strange word there. Some people are like, why isn't it derivatable? Meaning you can take the derivative. And that's a fair question. It has to do a lot with the history of mathematics, some of which I don't know very well. But I don't know if I told you guys this last week, but this is called the difference quotient. And so if you can, that's why it has different in it, because it's the limit of the difference quotient. Okay? You don't need to remember that, but if you're ever like, why did they call it that? That's why. So let's find the derivative of f of x equals x cubed. So that's going to be the limit as h goes to 0 of f of x plus h, so that'll be x plus h cubed minus f of x, which is just x cubed, over h. Every derivative that you ever do will start off as an indeterminate form for the limit every single time. And it's always a 0 over 0. So we've got to do something to make it to where it's not 0 over 0 so that we can evaluate this. So with polynomials, what we typically do is we just expand that. So that's going to be the limit as h goes to 0. And someday when we have more time, I'll show you how you can do this really, really quickly. This is going to be x cubed plus 3x squared h plus 3xh squared plus h cubed, then minus x cubed all over h. There's a trick to that called Pascal's triangle, but I don't think you guys have ever learned it. You did learn Pascal's triangle?
We had to learn for academic math class.
Gotcha. I was like, should have done it either in Algebra 2 or Pre-Cal, but I don't know exactly where you would do it. Anyway, simplifying that, that'll be the limit as h goes to 0. Notice that the x cubed and the negative x cubed zero out. Everything else in the numerator has an h in it, so I'll go ahead and divide, and I'll have 3x squared plus 3xh plus h squared. Let h go to 0, and the second two terms both drop out, and you get 3x squared is f prime at x. In other words, that would be the formula to find the slope of the curve, or the slope of the tangent line, they're the same thing, at any value you wanted to. All right. Any questions about how to do that? All right, there is an alternate definition of the derivative. The derivative of the function f at the point x equals a is the limit f prime of a as x approaches a of f of x minus f of a over x minus a. And you're like, wait a minute, why is that? So basically, you don't have to draw this if you don't want to, but I'm going to real quickly. If I have a function y equals f of x, and I'm interested in the derivative at a point a f of a, I can pick any other point on here x f of x, and draw in that secant line, and this would be that slope, right? F of x minus f of a over x minus a would just be that slope. But then if I take the limit as this point x gets closer and closer to a, what I end up with is, oh, that was really horrible. I thought I had turned on my straight line tool. You end up with that slope. As x gets closer and closer to a, you get closer and closer to this slope, which is the slope of the tangent line or the slope of the curve at that point. It's just a different way to write it. Sometimes this is easier. More often than not, we use this, but every once in a while the other one is easier. So let's do this one. And I'm going to change this. I admit to put in a constant. And let's put in something that'll work out nicely. Let's say f prime at 9. So f prime at 9 will be equal to the limit as x goes to 9 of f of x, which is the square root of x, minus f of 9, that's the square root of 9, over x minus 9. Again, as promised, if you try and evaluate that, it's going to be 0 over 0. We've done several of these in the first unit. Do you remember how to simplify that? By? Yes, multiply both the numerator and denominator by the square root of x plus the square root of 9. Thank you very much. When we do that, we'll have the limit as x approaches 9 of the numerator will become x minus 9. The denominator will be x minus 9 multiplied times the square root of x plus the square root of 9. The nice thing about that is the x minus 9's divide out. And we'll have the limit as x approaches 9 of 1 over the square root of x plus the square root of 9. Now I can evaluate that. That'll be 1 over the square root of 9 plus the square root of 9. So it'll be 1 over 3 plus 3 is 1/6. The alternate definition is nice sometimes when you have, like I said, it's certain kinds of problems that it works on really well. Okay, things with square roots in them, things where you have a complex fraction, it works pretty well in those also. All right, let's move on. Any questions about that? All right, notation for the derivative. This also has a lot to do with the history of math. Calculus was actually developed primarily, at least, not entirely, but primarily by two different people living in different places at almost exactly the same time. So you've heard of Isaac Newton. Yeah, it's from time to time. So he was working in England, obviously, but you probably have not heard of Leibniz, who was working in Germany on calculus at the same time. Equally good stuff. Newton's more famous for two reasons. One is because we speak English, and two, because he did a lot of work in celestial mechanics, like gravity and those sorts of things. Right? Leibniz was more of a pure mathematician. So each one had their own way of writing things. It'd be like if you came up with addition and I came up with addition, and we had to come up with a symbol for addition, and you picked one symbol and I picked something else, right? To honor them, and because, well, one of them is easier to write and one of them gives you an idea of what's going on, we've kept both of them, okay? So anytime you see a prime like this, f prime, y prime, for the derivative, those are Newton's way of writing it. It's not important that you know that those two go with Newton, but he liked primes. Leibniz liked doing it this way. The nice thing about Leibniz notation is, although it takes longer to write, when you write dy dx, that reminds you that this is a slope. It's the change in y over the change in x. Okay? That's the advantage to Leibniz notation. It also, a long time from now, it's going to make some other things make more sense than Newton's. So you need to be familiar with all of these. Which ones do you see the most? Probably f prime of x more than anything else, but need to be familiar with this as well. All right, so estimating what the graph of a derivative looks like from the original function. So what we're going to want to do here is at each of these points that they've given us, which correspond to x is 0, x is 1, x is 2, x is 3, and x is 4, we want to estimate what the slope is. We're going to put them on this graph, and then we're going to stitch those points together. There's one over here that's really easy to estimate. At 4, if I was to draw a tangent line at that point, it would look like this, right? What's that slope? 0. So at 4, the derivative, which is the slope, is going to be 0. For the other ones, we need a quick way, and I don't want you to, when you're doing these, don't spend a real long time doing them. At first, you'll have to spend a little bit of time, but it needs to get to the place where you're just graphing these pretty quickly. So what I do is this. I draw in a little piece of what appears to be a tangent line. Now, if you've got something you can use as a straight edge, that is the best thing you can do. I'm going to put mine up here, and then I'm going to use it to draw my tangent line. And so my tangent line looks something like that. It almost hits this other point. And what I'll do is I'll go to the right one and then estimate how much did that go up. Because slope is the change in y over the change in x, I've just drawn a little slope triangle. So this was 1, and this went up 1, 2, I don't know, 2.5? Okay, I think it's a little less than that, but that's okay. So it's at about 2.5. Then I'll do that for the next point. I'll use my straight edge to help me draw a line that is just skirting through this. And I'm like, okay, went over 1 and went up. If that's 0.5, went up about 1.5? Yeah? So about 1.5. Now, for this next one, it looks pretty close to 0, doesn't it? If you drew a tangent line through it. So that it just kind of skimmed through. I think it's slightly negative, though. And I'm not even going to bother drawing a slope triangle for that. It's very slightly negative. Slightly negative. When we get to 3, though, this is pretty steep, and it definitely has a negative slope. Looks sort of like that. And again, I'm going to do a little slope triangle where this goes over 1. So my change in x is 1, and my change in y is about, well, I don't know, that looks like it's about a half, up to 2 point something. I'm going to say this is a little over 2.5, and it's clearly a negative. So I'll be down here at negative 2.5 or so. I never know how far I'm going to go up or down. I always go over 1, though. So the denominator of my slope is always 1. That makes it easier. So in every one of these, I try to make the horizontal part be 1. Then I don't have to go, well, this is about 3.8 divided by about 2. Now I've estimated twice, and then I'm dividing, and now it's horrible. Okay? So that's a good question. So I'm just going to stitch these together and go, okay, this looks sort of like that. And then over here, the slopes are clearly positive, so I'm going to go, yeah, it does something like that. If I ever give you one to draw, it's going to be something where it's like, I'm going to look for the basic shape. Do you have where it should be positive and where it should be negative correctly, and where it should be 0? That's it. I'm not going to go, well, you said the slope was 2.3 here, and it's actually 2.5. Sorry. Okay? We're just estimating, which makes some students absolutely cringe. They don't like to estimate things. All right, page 3. We can also estimate derivatives numerically. So it says use the following table of values to estimate f prime at 3.2. Notice no information is given to us as to what happens at 3.2, right? So what I'm going to do is I'm going to choose the interval that contains 3.2. That's the smallest interval that contains 3.2 on this table. I could do bigger intervals, but I'd like to stick as close to it as possible. And all I'm going to do is find the slope on that interval. F prime at 3.2 then is going to be approximately 30 minus 26 over 4 minus 3. So it's about 4. How confident am I that it is 4? Oh, not at all. It could be 6. I doubt it, but it's probably closer to 4 than that. But there's no telling what's going on in between those two. But this is my best estimate. Given the very limited amount of information that you have for this, that's the best estimate that we can give. And it could be because, we think, oh, well, this is going up the whole time. What if between 3 and 4, it went up to 4 billion and then back down to 30, right? My slope at 3.2 is probably not at all 4. But again, given what we have, this is the best estimate that we can give. It may be a great estimate. It may be the worst estimate ever. Okay? All right. That is it for today's lesson.